Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. I will present our paper entitled on linear mappings in crane spaces that preserve orthogonality. Background of our research is Wojcik's paper that discusses operator that preserves squilinear and semi-inner-product form. The paper is a development of the results obtained by ICMSCE, which is about linear mapping that preserves approximation orthogonality in in-product space. Our main focus is theorem 6 that's in Wojcik's paper that say that x and y be two inner product space over C. For non-zero mapping T from x to y, the following statements are equivalent. 1. T linear and there exists gamma larger than 0, such that for all x in X, we have norm of Tx equal to gamma times norm of x. 2. There exists gamma larger than 0, such that for all xy in X, we have inner product of Tx and Ty is equal to gamma squared times inner product of x and y. 3. T linear and strongly orthogonality preserving. 4. T linear and orthogonality preserving. Let V be an inner product space over F. It can be complex or real. The development of the concept of inner product has been carried out in various directions, including the following directions. First, sesquilinear form. 2. Indefinite inner product space. And 3. Binaire form, which is a generalization of indefinite inner product space over real by expanding the field to anything. It doesn't have to be real. The problem is, how can the theorem in Wojcik's paper, as you can see before, be applied to crane space? Now, I will present you some terms and definitions. First, the definition of indefinite inner product space. Let V be a vector space over C. A function bracket from V cross V to C is indefinite inner product space on V if the following conditions apply. First, linearity of the first argument. 2. Antisymmetry. 3. Non-degenerate. Second, definition of crane space. An indefinite inner product space K with indefinite inner product bracket is a crane space if K can be rewritten as orthogonal direct sum of K plus and K minus, where K plus and K minus are Hilbert space. Any such representation is called a canonical decomposition of K. The definition of orthogonality preserving map in a crane space. Let X and Y be two crane space. A mapping T from X to Y is orthogonality preserving for all xy in X capital. If X orthogonal to Y, then Tx also orthogonal to Ty. And it calls strongly orthogonality preserving if all xy in X capital X orthogonal to Y, if and only if Tx orthogonal to Ty. This is our result. Lemma 1. Let X be a inner product space and Y is indefinite inner product space. Let C from X to Y be a linear mapping that preserves orthogonality. If there is X in X capital, X not equal to 0, such that indefinite inner product of Tx to itself is larger than 0, then image of T with indefinite inner product space on Y is inner product space. Corollary 2. Let X be a inner product space and Y is indefinite inner product space. Let T from X to Y be a linear mapping that preserves orthogonality, and there exists X in X capital, X not equal to 0, such that indefinite inner product of Tx to itself is smaller than 0. Then, image of T with negative bracket is a inner product space. Lemma 3. Let K be a crane space and K is as the definition before, can be written as orthogonal direct sum. There exists x in K capital, x not 0, where indefinite product of x to itself is larger than 0. There exists K1 plus and K1 minus such that K can also be written as direct sum of K1 plus and K1 minus and x in K1 plus. Lemma 4. Let x and y be two indefinite in the product space, and x is a Green space. Let T from x to y a linear mapping that preserves orthogonality. If there exists x in x and x not equal to 0 and indefinite in the product of Tx to itself is not equal to 0, then there exists gamma such that for all x in x we have indefinite in the product of Tx to itself is equal to gamma times indefinite in the product of Tx to itself. And this is our last result. Theorem 5. Let x and y be two Green spaces, and Tx is a mapping from x to y. The following statements are equivalent. 1. T linear and there is gamma not equal to 0, such that for all x in x, we have indefinite inner product from Tx to itself is equal to gamma times indefinite product of x to itself. 2. There is gamma not equal to 0, such that for all xy in x capital, we have indefinite inner product of Tx and Ty is equal to gamma times indefinite product of x and y. 3. T linear and strongly orthogonally preserving. 4. T linear, orthogonally preserving, and there exists x in x capital where indefinite inner product of x to itself is not equal to 0, and indefinite inner product of Tx to itself is not equal to 0. So the conclusion of our research so far is that theorem 6 that you can see before and is in Wojcik's paper can be applied to Green space with a few adjustments. And this is our references. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.